I'm Neil, and welcome again. Today's chapter is on circuitry. Here's a picture of the United States lit up. It's a satellite image from space, and it's only with this vantage point can you see the effect of our grid system. It just really lights up billions and billions and billions of watts of power. This, of course, is unfortunate in one sense, in that much of this power it's being supplied by non-renewable sources. The burning of fossil fuels, for example, which is not sustainable. Alternative sources have yet to catch up. Things like solar power, and hydrothermal, geothermal, wind, nuclear power, etc. Now, there are other countries that almost predominantly get their grid system functioning from renewable sources, but the United States is yet to catch up with that. We only account for about 5% of the world's population, but we use 25% of global energy every year. And again, that's not sustainable. I suppose much can be said along the same lines for other developed countries as well. But that's a topic for environmental science. Today we're going to talk about the circuitry, the basic circuitry that goes into generating power and power supplies. Now, if we take a look at the chapter of interest, so we start this chapter by defining with diagrams as well some of the basic components that you'd find in a common circuit. Things like the battery source, of course, the power source, capacitors, switches, ammeters, voltmeters, resistors, galvanometers, and those kinds of things. And we show how they're all put together in a basic circuit. And so the description of, again, if you're an electrical engineer, you're taking a physics course, this is the most important chapter, one of the most important chapters to your budding career. So, for example, this one diagram here, it shows one load as a resistor on the circuit. It shows the battery and how the potential, the high potential, and the low potential sides are determined, and how the electric field points, the direction of the electric field, and the Coulomb force that it exerts on the electrons, the conduction electrons in the connecting wires. And it shows that the direction of the flow of the charges, in this case electrons, is exactly the opposite to the flow of current. You see, hundreds of years ago, before we understood that it was actually electrons, negative charges that were moving, that generated electric current, we simply assumed, or they simply assumed, that there were positive charge carriers. So that convention still holds today, where we take the opposite direction, that is the direction of the flow of positive charge, as the direction of the current flow. But the reader should take note that the actual flow direction of charges is opposite to the direction of the current, if the charge carriers are electrons, that is. So what happens when these charge carriers, when they encounter like a resistor, for example, they lose some energy if you follow the direction of the current flow, but they gain energy if you go against the direction of the current flow. So all of these things are described in some great detail in this chapter. And as we scroll down, there are numerous circuit diagrams in this chapter. After all, it's just a chapter on circuits and circuitry. So it's predominantly what's discussed. Again, if you're a budding electrical engineer, this is of great importance to you and your career. And we look at what happens when there are multiple resistors in the same circuit. Resistors can be wired in series, where they go one after the other, so the same current must flow through, but the potential is different. Or they can be wired opposing each other, and some examples are done with this is called series wiring. And there are, as with everything in life, there are pros and cons to everything. And one of the downfalls of wiring a circuit in series is nothing more than Christmas lights. So showed a bunch of pictures, random pictures. In Europe they use a different grid system. The power is generated differently, and it's the outlets measured, 220 volts or 240 volts, as opposed to the United States where it's 110, 120 volts. So the power system is different. So I chose a few pictures from around the world of some of my trips. This is in Lapland. This is in Sweden. Christmas market in Sweden. And based on how the power is generated and measured in Europe, for example, I showed a few more. This is in Amsterdam. Amsterdam is not really known for celebrations of Christmas. They're known for other choice things. But again, that's a different story. Here's one in this is in Munich in Germany, the Christmas market, and so it's just different ways of how the lighting system works. And so there's a method of madness here. I discuss how the different grid systems and power is generated in different places in Europe, for example, and derive some equations to show how to interpret the wiring of circuitry in different places, how the power is generated. For example, wiring Christmas lights, like we just saw, in series means that if one bulb goes out, because the resistors are in series one after the other, if a bulb goes out, then everything beyond that point stops, because the same current has to flow through each resistor, because the current has nowhere else to go. So the lights all go out until you change that one bulb, for example. But nowadays, wiring has come a long way, and they've mitigated that problem by how they've wired the circuit. So if one light goes out, all of them don't go out. But old school Christmas lights, they work on this principle. Another method of wiring circuits with these resistors is to instead of putting them one after the other in series, we can put them such that they oppose each other. So as the current enters this junction here from the battery, the current actually has a choice, and it splits. Of course, the current that splits here, once they meet back up at this point here, this current here must equal the current here. So what comes in is what goes out. That's the conservation of a charge, because after all, the electric current is, its constituents are electrons, and the electrons simply can't vanish from the wire. So what goes in must be what comes out. But current will choose the path of people. They will choose the path of least resistance. So if you've got two resistors wired in parallel, for example, the larger current, and they'll split equally depending on, I shouldn't say equally, they'll split depending on the value of the resistances. So the larger quantity of current will choose to go through the lower value of resistance, and the smaller current will go through the higher resistance of the resistor. That's because, again, the current will choose the path of least resistance. So because they're wired in parallel, the current splits, but the same potential applies to both. So unlike being wired in series, where it's the same current going through each resistor, the potentials are different. In parallel, it's just the opposite. The current splits, but the potential across each is the same, which is equal to the potential of the battery, by the way. Right? So the current in each resistor is equal to the potential of the battery. Whereas in series, it's the sum of the potentials of all the resistors will equal the potential of the battery in the circuit. So all of these things are derived mathematically to find the equivalent of the total resistance, the net resistance in a circuit, depending if it's wired in series or in parallel. And again, there are multiple examples of wiring structures. As you can see, one interesting looking scenario here, and we can find what the net resistance is between any 2 points, for example, point A and point C, or point A and point D. It's the same circuit, but the reader, I think, would be interested to know that the net resistance, or potential rather, between 2 points depends on the path taken. And the reader will see this. And I show step by step how to take a circuit like this and break it down into something that's simpler in order to calculate the net effective resistance. So all of the details are shown for the reader until we end up with one equivalent resistor. So this actually, all of that comes from that. So And there are multiple examples of these resistors and how they're wired differently. And there's an example here with, let's see, there are 5 different resistors in the circuit, and some are in series, some are in parallel. And we can calculate just randomly the current going through any one of these resistors. So that will require breaking down the circuit into something simpler. So I show step by step how we can break down these circuits into something simpler for the reader. So each diagram breaks it down to one step that's simpler until we end up with all resistors in series, and we can simply just add them all together to end up with one. So this circuit here is actually the breakdown of that. So we take something that's somewhat complicated and we make it quite simple. Right? So that's what this chapter is, really all about. That brings us to Kirchhoff's laws. Gustav Kirchhoff, he applied 2 conservation rules here: the conservation of charge and the conservation of energy for the charge carriers, the electrons. The conservation of energy applies to the potential between any 2 points in a circuit. So when circuits can't be broken down into anything simpler, Kirchhoff's laws will always work. And one is the Junction Rule, which deals with the conservation of charge, which, as I mentioned earlier, if the current splits in a wire, then the sum of the 2 partial values of the current must equal what came in the first place. That's a conservation of charge. So in any junction of a circuit, we can apply the Junction Rule. What goes in is equal to what must come out. And the other rule is the loop rule, which is a conservation of energy. So we can account for the energy throughout any loop of the circuit, or between any 2 points for that matter. In the direction of current, if you looked at a single electron, the charge carrier, as the charge carrier goes from the low potential side, the negative terminal, to the high potential side, the positive terminal, it gains energy. When the same charge carrier hits a resistor, and again, if we're looking in the direction of current flow, it loses potential as the product I times R, which is the value of the resistor. So energy is lost as it goes through the resistor, but the energy is regained as it goes back through the battery and gets recharged. So a perpetual motion machine, if we ignore any losses in terms of heating or any kind of dissipative heat losses, for example. So the application of the junction rule and the loop rule are applied in several circuits. And again, the beauty of Kirchhoff's laws is that they apply to any circuit, especially the ones that can't be broken down into anything simpler. In particular, when we see things that get a little bit complicated here, where you've got multiple batteries, for example, and they're oppositely opposed and the current's flowing in opposite direction, that seems to get quite complicated. But I assure you, there's a stepwise methodology in solving what seems to be complicated problems, and the reader will get all of this from this chapter. So it's going to be quite useful, and it's quite a powerful tool, actually, Kirchhoff's rules. And as with, you can see the circuits are getting more and more complicated here. We're applying Kirchhoff's loop rule more than once in the same circuit, so that's also a very useful method to apply. So the solutions to many of these problems are done in painstaking detail for the reader. So at the end of this chapter, the reader is going to hopefully have a very good understanding of how to solve for the net resistance in any circuit with multiple resistors, depending on how it's wired, the pros and cons of wiring either in series or parallel, and the applications of the conservation of charge and the conservation of energy in Kirchhoff's loop rule in solving for circuit problems. Once again, I thank you for your time. Bye-bye.